All right, so I see that we have participants slowly joining back into the call. Without any further ado, let me introduce you to Dr. Oscar Mondragon, who would be doing workshop one today until 4:30 p.m. So Dr. Mondragon is the director of MS in Software Engineering, Computer Science Department at the University of Texas at El Paso. Thank you, Dr. Mondragon, for agreeing to conduct the workshop for all of our participants. The floor is all yours now.
Okay, good afternoon, everybody. Can you hear me?
Yes, I can hear you. Yeah.
Okay. So let's start. So this afternoon part is split in two parts. In the first part, the first hour and a half, we are going to be talking about supporting development of complex systems through modeling and simulation. And on the second part, we are going to be talking about on model-based systems engineering. So the intent of this talk is for us to understand what a model is and then what a simulation is. And talking with some people from industry, and also I was providing consulting some years ago. And one of the main problems on using the models is that some people forget what the intention of the model is. So what the purpose of the model is, or what do you do with the model? So um, in some organizations, they may be using the models, but they don't know the purpose of the model. Or they may be using the models, they may be creating the models, but nobody's using the models. So they are using those models as in order of process compliance, but they are not really taking advantage of the models. So the emphasis of this presentation today is for us to try to understand the meaning of a model and a simulation. What are their characteristics? How do they interrelate models and simulation, and what are they important? And how do we build some of those guys? And when can we apply them? Okay, so let's start. So what's a model? It's an abstraction or representation of a system, entity, phenomenon, or process of interest. Um, I'm going to remove my camera just to prevent some bandwidth issues. So sorry, I'm coming back. So we have a model, and what can we use as a model? So this table might represent a model. So over here, we are trying to represent some behavior where we have a current state and a new state and the type of event that we are getting in order to pass into the other model. Now, we may also have different types of models or forms of model. So your model can be mathematical, logical, physical, or have some procedural representations. So here we have a tabular representation on the top part, or we may have some drawings such as the PetriNet model, okay? The other important thing is what is going to be the intent of your model. So you need to identify the characteristics or aspects that you want to represent for the entity system that you want to understand. So systems engineering may use the models to represent the system and its environment. This is very important. So the system is not there alone. You are going to put that system in an intended environment, and it's important that you consider the environment when you are modeling your system. And you will use this model to analyze, specify, design, and verify the systems, okay? And the other important thing is that you may have different type of models, and each one of those models may have a different purpose. So it's important that you understand how many models you have and what's the purpose of each one of those models. So like in this example, On the top part, we have a table for straight state transition, and on the lower part, we have a visual representation of those states. So here, I care about the different states the system may have and how do I transition from one state to another state. Whereas on the PetriNet, what do I care is the multiple events that may happen at a given time, and if I might be able to execute or not concurrent executions or paths. And if I have concurrency, in what point do I put them back? So I can use forks or I can use joins. Now, on the principles of the model, one of the first things that we need to do is to clearly define the purpose of the model. So sometimes people will ask you, yeah, let's model it. Let's have a model. And before you start, you should ask yourself, and what do I want to win from doing this model? What's going to be the purpose, okay, of that model? So important things is that you may have different type of models and you can use different models through the different phases in your life cycle. So you may use it to characterize an existing system or a new system. You may use it during mission analysis process. You may want to reach the concept formulation and evaluation. You may use it during architecture. You may use a model to help you do the integration of your system. You may use a model for verification purposes. You may also use a model, for example, to support your training, or you may use the model for get together all the knowledge that you have about that model. You may use it to validate your understanding of whatever you are doing, okay? Now, continuing the purpose of the models, so what the model represent? Mainly, you will focus on some characteristics. It's very difficult to try to put all the characteristics in place and try to model them. So most of the time, we are going to use abstraction. We are going to focus on a set of characteristics. Also, you need to consider the environment of your system of interest. And also, you need to understand the interactions of that system of interest. Now, as we were saying before, those models can be used through all the phases of the life cycle model. So as we were saying before, we can use it for mission analysis. During requirements, we can do it at both levels. So we can do it at the stakeholder requirements. So maybe we want to use some use case representation, or I want to do it as a system definition requirements. So I maybe use some more technical diagrams as the one that the previous speaker Yvonne was showing with us. So she was using state transition diagrams or activity diagrams. We can also use models to define the architecture and use some of those frameworks for architecture and the different views that you need to generate for architecture. We can use it to do system analysis and help us on the verification and validation, okay? And so what we have on the right are some of the processes that we use according to ISO 15288 is the standard for systems engineering lifecycle processes. On the technical processes, we have 14 of them. And here we have the first 5 processes from the technical process group. Now, on the scope of the model, okay, it's when you are doing this model, you need to consider 3 important things in order to achieve your purpose. What's going to be the breadth of your model? What's going to be its depth? And what type of fidelity do you want for your model? So on the breadth, it's how many different aspects do you want to consider in the model? Are we okay just with the functional decomposition, or we also want to define the interfaces? I also care about performance, or do I care about some other non-functional requirements or quality requirements? On the depth, it's at what level do you want to do your model? Do you want it to do it at the system level, or do we want to do at the subsystems levels, or we want to get down and do it just at the element level? And the fidelity part, it is how much attention or how many characteristics or how many relations do we want to consider? So those three levels, those three things, sorry, the breadth, the depth, and the fidelity are going to impact how do you develop that model. And it also is related to the intended purpose of the model that you want to build, okay? Another important thing is that when, when you are working in developing a system, most probably you will not do only one model. Most probably you will do a couple of models. So for example, you may want to understand which are the operational modes of the system. So then you have it at the system level. But then you may want to understand what are the um, states within a given subsystem. But that subsystem may have a couple of components. So later on, you may want to understand the behavior of a given component. So the same model can be used at different levels of abstraction in your system decomposition. So how do we start? We should start with a mental model, do a couple of sketches, and then elaborate that and transform that until you reach a final model or your simulated product. So as an example, what we're saying here, you can start doing some sketches, and those sketches are going to be done based on what type of model you want to do or what domain we are talking about. And continue doing your sketches until you start converting it into graphics or images, or you start getting some emulations, or you start building some mockups, or you do some models, or you go all the way into getting your prototypes, okay? Now, you may also consider, as I was saying before, that we can do more than one model. So we can have one model for different point of views. So let's do one model for functional decomposition. Let's do one model to understand the states and the behavior of the system. Let's do to understand how reliable is our system, or whether or not we will be able to use some of the functionality of the system. Now, talking about syntax and semantics, this is a very important aspect of the models, and is going to be what distinguishes from informal models or from the textual representation. So your model should have semantics, and it is the intended meaning of the model, okay? It is like when we are talking right now, I'm making a sentence and you are getting some understanding of that sentence, okay? Why? Maybe because you know that the sentence should have a subject, a verb, and then a predicate. Now, talking about that, we also have components and rules that help us to convey the intended meaning. So on the syntax are the different elements that you have to build your model. In the case of the Petri net diagram, we are using the places, we are using the transitions, and we are using the tokens. And so in this case, for example, we have a place that has two tokens. The tokens are the events. And what this diagram is telling us is that in order to fire this transition, I'm on the right part of the model, so on P1 and T1. So in order to fire T1, we need two tokens from place number one. So the tokens, remember, are events. When I get 2 events, I'm going to fire the Petri net. And 2 of those tokens will go to place 2, and only 1 token will go to place 3. And here we are forking the, the flows of my process. Okay, so that's one of the examples. And this is why it's very important to have the syntax, understand each one of the components, and then when you put them together, what's the meaning of the whole model. Now, one important question that all of us should ask is, if I have so many models, which model shall I use? Okay, so this is very important. So first, consider the goals that you want to achieve of doing the model. That's the first thing that you have to do. So don't get a model and then try to see how that model can be helpful to you. No, first ask yourself, what do you want? What's your goal? And then once that you have the goal, you can ask yourself, what's the purpose? So for example, what knowledge you want to convey. Another important thing that you may want to ask yourself is, who is your audience? So who is going to consume that model? And talking about validation aspects, and this is one of the topics that I was asking Yvonne in the previous talk, is who's going to be your customer? Is it going to be a technical customer, or that customer really doesn't know and will not be able to read your model if you do not explain the model? So that's very important. The fact that the customer doesn't know the semantics and the syntax of your model doesn't mean that they cannot learn. And we can approach them and we can kindly explain them the syntax and semantics so they can understand our model. Okay? Please do not use the models to impress your customers. Okay? Do not threaten your customers, especially not technical customers, by trying to impress the people with your model. That's the worst thing that you can do in your professional life. So remember, you want to validate your understanding. So it is in your best interest that the customer can understand your model. Okay? Now, here we will continue on some examples of taxonomies for models. So when we're looking in the literature, there are many different taxonomies. So in the one that we have in front of us, they talk about abstract models and physical models. And the physical is going to be the representation of an actual system. As an example, we can have a model of an airplane, or we can have a wind tunnel, okay? On the abstraction, they are telling us that they vary a lot in the degree of formalisms that they may have. On the informal models, you can do a sketch. All of us may be in the need to represent something, and we just start drawing things, and we can give it to one of our colleagues. So that's okay, it helps us to try to put our ideas down. But be careful, because nowhere we explain what the symbols mean. And when we have those sketches, maybe we have some intended meaning of our diagram. And when somebody read that sketch, may have a different interpretation of the diagram. And that may happen because we are not being clear on the semantics and the syntax of the elements that we use in our sketches. So we are better off if we move into a formal model, yeah? And examples of formal model, it can be geometric, quantitative, and logical models. In another taxonomy, this is from the System Engineering Book of Knowledge, they talk about the descriptive models. Now, in those ones, we are trying to have the relationships between the components. For those of you that know UML, a class diagram is a descriptive model. A sequence diagram is a descriptive model. On the analytical models, we want to have the, we want to represent the mathematical relationships between the elements. An example of those are differential equations. We can further classify it into the dynamic models or static models. And dynamic models are the ones that are time dependent. So if we want to do some calculations of acceleration, so then we need to take into consideration the time or the velocity. Yeah, those might be some of the examples. Now they say that we also have domain specific models, and they can be, again, descriptive of analytical. And each one of us in our own engineering field, we know some of those models. And those descriptive or analytical models change based on the application domain that we are working on. Now, talking about the system model, they are telling us that you can also have descriptive and analytical models or and analytical models. Those models can span through different domains. So let's talk about a car. We may have models for mechanical, from the mechanical engineering point of view. You may have models for electrical engineers. We may have models for software engineers. So each one of the disciplines may have its own model. Now, the important thing over here is how do we merge those different point of views from the different domains? How do we make them cohesive? Because they need to be consistent. We cannot be representing two different versions of the truth. Now, on another classification, this is from the standard 15288 from software and system lifecycle processes. They talk about functional models, and here we care about the different set of functions that a system can do and the interfaces that they may have. They have behavioral models when we may care, for example, about the state transitions, or we may care about the sequence in which the events are sent, or we might be talking about Petrinet, it's another behavioral model. Temporal models or time-related aspects. I had the opportunity to work with future interval logic and linear temporal logic. In those ones, you might express conditions of the system and saying between this interval of time, this event is going to happen before that condition arrives. So those might be examples of the temporal models. We also have structural models to represent the physical parts of the elements, mass models to represent spatial placements of the models. Another example is the network model. Here you will have your components and what are the relations between those components, what's the flow of events between those components. And we may also have the layout model example, okay? Now, let's talk a little bit of what's a simulation. And it's going to be an implementation of the models in a specific environment. And the other important part of the definition is that it allows the model execution over a time. So we are executing the model that we have. As an example, we may have this airplane, and we are trying to understand, the aerodynamics that we have over the airplane. How is this thing affecting the airplane? So do we have enough structural strength into the wings or not? Are they going to fall apart? So that's one of the things that we may want to put over there. Now, those simulations will provide the means for analyzing complex dynamic behavioral systems, people, and physical phenomena. Another example of a simulation that I had the opportunity to work at UTEP, in the electrical department a long time ago, it was this problem that they have. It was just parallel programming coming into place, the first operating systems managing multiple programming. Uh, but what they were saying that there are certain applications that demand a lot of high computation. And rather than leaving it to the operating system that doesn't know anything specific to that application, it would be better if you create your own microprocessors, specialize the microprocessors, understand the flow of events for these high demand computational problems, like the dynamics of fluids, And then they were saying, yeah, let's understand the problem, let's understand the flow, and let's create the architecture that will have a better performance using those flow, those computations. So we were working on architectures that may have around 400 microprocessors, and they will have different type of memories and different types of microprocessors for doing simple operations or uh, doing a fork. So for example, if you want to do a matrix operation, you will have to do a pipe of 4 microprocessors to conduct the matrix operations. But then they realized that they needed many of those. So you can have a fork to have multiple um, matrix multiplication simultaneously, and then using a join to get all the values back, and then sending that information to a temporal memory. So it was a really nice experiment where um, we were first creating the layout, and then we will have a simulation that will use the layout of the architecture. It will use the programming instructions for each one of the microprocessors, and then we will run the simulation. And in that simulation, we wanted to know if it was some bottleneck for manipulating the information. And then how can we modify the architecture so we can get a better performance on the flow of events, okay? Um, Another important thing is that your simulations doesn't have to run in a computer. So in the example that we have over there, we have a wind tunnel. That is another example of a simulation. Now, in this example, sorry, for running a simulation, we have an analytical model. In this case, it's going to be an executable code. And you will need some inputs. So you need some conditions and you need some data that you are going to put in back into the simulation. And then you need engine. So that engine is going to execute your code, is going to be using the inputs, and then it will run the model over a given set of time, and then you will have your outputs. In the example that I was sharing with you guys, our analytical model that we were putting over there, it was the programming instructions for each one of the microprocessors. The other inputs that we were giving into the model was the layout of the architecture and the connections between the architectures, okay? And then we were giving the flow of data that was passing into that simulation. Then we have to create that simulation, and that simulation will allow you to see each one of the microprocessors with different colors. And the colors will represent whether or not they were busy doing calculation, they were in standby waiting to be used, or if they were waiting for the next microprocessor to be ready to release the data. So in that way, when we were running the simulation, we can see the different colors of the microprocessors, and based on the colors, we were able to identify the bottlenecks on the on the architecture that we were doing. Now, let's get into identifying the goals of the simulation. So if you are going to use a simulation, most probably you want to investigate, verify, and validate the system's behavior, you know? And that system behavior or that system is going to be placed into an environment. So you are validating the system behavior using some context, okay? Now, let's see how can we use those simulations, some of those goals. So some people may want to use the simulations to understand the performance of a given device. In the example that I gave you before, we wanted to see how fast was the execution of the architecture that we built. You might also use it for uncertainty reduction when you are making decisions. You might also use to determine the level of risk in the system that you are doing. Some people will use a simulation just to validate your understanding. Okay. Some other people, this is a common use when you are doing during requirements solicitation. Sometimes the customer wants us to do something, but we are not sure if we can do it. So then it's going to be a good idea to see if with the resources that we have, we can achieve the type of performance that they are asking us to achieve. And by doing the simulation, we might be able to let them know if we can fulfill their requirements or we will not be able to fulfill it. Okay. Now, talking about the operation of your simulation, so we have those scenarios. It may operate in real time, your simulation. So what does that mean? That you need a live operator in the loop while you are running your simulation. Um, the simulation that we did for the microprocessors, in that one, we didn't need a, we did not need an operator. It was kind of automatic, and as the data was processed, we could see what happened with if the microprocessors were in use or they were just waiting for somebody else to work. Now, another example is that they may operate faster than the real time. So sometimes an operation in real life might be done every hour, and you want to know how many operations your system can do before it breaks down. So you cannot wait an hour every hour to do one trial. So you may want to adjust the frequency of all those events and use it in your simulation. And then you can do hundreds or thousands of those simulations and not to wait into the real times. And then you might be able to get some results faster. And you may also use artificial intelligence when you are doing that. And the artificial intelligence, what's going to do is that for some of the executions, looks ahead. And if the probability is low, it's going to prompt the search in one of those paths and it's going to change to another path. So that's kind of cool and it's okay. But when you do that, it might be some occasions where you might not find a response. So sometimes it's good, it may have some of the problems. So one person was sharing with us that they did one of these models for one of the jail systems, and they did the model. They were having troubles with the available beds for the inmates, and it was a huge place, and they were trying to use this model to have a better assignment of the beds to the inmates. But they were running into the problem that because of the artificial intelligence was running all the searches, it was times where it will say that it was no bed available when in actually in some of them were available. Okay, now let's talk about physical simulations and get some examples. We might use some physical simulations to replicate a small number of attributes. the important thing over here is that even though it's just a set of attributes, we want to get a very high degree or accuracy and modeling those small parts. When can we use that? When we want to get the behavior of those, some of those attributes within a given environment. Building those type of models is very costly, you know, and the number of events that we can use might be also very reduced. And what also we need to understand is that there are certain problems that are easy to solve, and there are certain problems that as you start adding the number of elements, the computational time to solve them kind of gets to the infinite, and they are called MP completeness class, these type of problems. Now, examples of some physical problems with reduced attributes might be the wind tunnel or some environmental tests, okay? Now, on the computer-based simulations, they might cover a broad aspect of systems attributes. So thanks to the greater computational power that we may have, we might add more attributes. We gotta be careful because even though with a high computational power, some problems, we still might not be able to handle all the variables. We may have models from different types of models, so different forms of models, and we will need to see the interactions between those different type of models, okay? Now, those models can be further divided. So those models of computation into discrete events, Monte Carlo events, continuous time solving models, and finite element models. Let me elaborate a little bit more into the Monte Carlo, okay? So it says use a repeated random sampling of input data on a model using randomness to obtain the results. So we are using some probabilistic aspects when we are building Monte Carlo. And it is good for complex models with couple degrees of freedom, significant uncertainty, non-relations, and it is probabilistic in nature. Now, when can we use Monte Carlo? And let me give you an example. In some organizations or in some situations, you may not have a history of the data. And let me give you an example. Maybe things are happening, but you are not measuring it, and therefore you don't have the data. So in one organization that I was helping, they wanted to know how many defects they were going to get into acceptance testing. And the reason of that is that the customer will not release the payment until they address certain percentage of those defects in acceptance testing. And they wanted to know like how much time they were going to spend fixing those defects. So the first part of the model, we need to try to predict the number of defects that they will get at acceptance testing. So what we did is that we start getting all the injection phases, and injection phases are the phases in your development cycle. And as humans, as we are working on those projects, you are injecting defects. I don't care if you think you are too good, you will inject defects. But if we train our people and we teach them how to use peer reviews and how to use a checklist, how to follow a process, then that team will also have the power to identify and remove defects. Now, by creating a model of all the injection phases and all the removal phases before acceptance testing, And using Monte Carlo um, to do the simulation, we were able to get some predictive value on how much errors we were going to get at that phase. So that's the point is that when we try to use correlations, because of the limited data that we had, we couldn't use it. So it's going to be some occasions when you want to use real data and you just don't have enough power on the data that you have to do any statistical analysis. Then as an alternative, you can use Monte Carlo. So once you run your models, you have more projects, now you start recording your data. Then once you have that, then you can try to move into a mathematical model. Okay. Now, another example, we have hardware simulations. In these ones, we need a human in the loop. So hardware or human in the loop simulations, they will execute in real time. You are using a computer-based models, okay? And it has hardware or a human element inside. So in UTEP, in the in the College of Engineering, we had the opportunity that Lockheed Martin has been taking some of those hardware simulations every year. And it's really cool, really cool to see them and to have a chance to play with them. So what about those simulations? They have a very high level of fidelity, and you can imagine that they are really costly to build, and especially when you are adding the visual uh, part in the model, or when you put the motion part in the model. Okay, so that's when they get really complex. Now, for some people may be working with projects related to the Department of Defense, and over there, they use three different names for the type of simulations: live, virtual, and constructive. And let's try to understand what they mean. On a live simulation, you need a live operator. And also the system is real. So live operators operating real systems. That's what they call live. Virtual simulations, you may have a live operator that is operating a simulated system, okay? And the constructive simulations are those that will use simulated operators operating simulated systems, okay? So those are the classification that they gave into the types of simulations. Now, another important thing is if you want to create one of those models and you want to put certain level of fidelity, then what do you do? Do you follow a process? And this is kind of, sometimes we use models during the development cycle of a system. But here they are telling us that for some of those models, you may have to follow a process, okay? So what they tell us is that treat it as a project. Apply configuration management to the sketches and representations that you are having. If you know how many sketches or representations you are doing, you may want to create a plan, okay? You may want to follow a life cycle process as you are creating your model. You may want to identify the risk of creating this model and have some mitigation activities. You may want to manage your model as a project. So that means that you identify all the people that is going to be working, producing the model, who is going to provide information, when are they going to do it. And one of the most important things is that make sure that you involve the experts, the domain experts in whatever model you are doing, okay? So we say a complete model or simulation can be considered a system its own, so treat it as a small system. And if it is true, then follow up system engineering lifecycle process, okay? And when you are developing your model or simulation, please plan and track as you will do with any other project, okay? Now, another aspect of models and simulations, it comes on the valid. So here's kind of the tricky things, okay? We can use models and simulations to do verifications and validations of systems. But here, let's step back. And here they are telling us, hey, and what about your model? So did you verify your model? Did you validate your model? In other words, can you trust your model? So while we are doing so we will have to do the verification and validation of our model before we use the model. And the verification, so we're asking how many characteristics are being modeled? Can you verify the model using those characteristics? That's on the verification part. And then on the validation part, we may ask the following. So who provided the information? So are they real experts? How much information was provided by the experts? Or maybe they were not really experts, so can we trust the non-experts? Okay. Another aspects is when during the development of a system, you have different models. And we may have different models at different abstractions, levels abstractions, but we may also have models from different application domains. Okay, so over there we have a challenge. And we may have logical models, executable models, quantitative models, okay? Each one of them with a different point of view and purpose, okay? So with all, and the other important thing is that we can have different models also at the different phases in your life cycle. So kind of start getting complicated, yeah? So different engineering disciplines, so the electrical people will use their models, mechanical, their models, software, their models, okay? And each one of the disciplines within each one of the phases of the development, they may also use different type of models, okay? So at the end, we must integrate those models and we need to ensure cohesion and consistency for those models in our solution, okay? Now let's get into some other examples. So here we have prototyping. It says enhance the likelihood of providing systems that will meet the user needs. They will facilitate the awareness of our understanding. So, for example, in software development or systems engineering, the use of prototyping is common. And we may want to, after we do, for example, customer requirements, we may want to validate our understanding. So in software is kind of common to do the mockups. And those mockups are kind of sketches of the user screens that the user is going to use as they are asking for a service. So they are asking for a service and the system is going to do several steps or certain functions. And as the system is interacting with the user, each one of that data provided either from the system to the user or from the user to the system, you can do the mockups. So to collect the data and to do the reporting of the or the views, and you can get a validation from your customer of doing that exercise, okay? And they may also have mock-ups or physical elements that we can show to the customers, okay? Now, talking about a little bit of history, when when they were using the word prototype some time ago, it says over here, it was the first of a kind product from which all others were replicated. And this is very common still on manufacturing. So on manufacturing, it's common that you have an organization that is getting customer requirements, understanding the purpose of the system. They do the analysis, the design, they go into implementation, and they create the first article. So that first article, it's reviewed, and they learn from that article that they create. They may even give some feedback and ask for some modifications. But the value of that first article is very important. And as we say on the second part here, it's not a draft. It was a complete product. But they do that before they go into mass production. And I think it makes a lot of sense and saves a lot of money. Okay. Now, in another way of using the prototype, as I was telling you before, you can use it on the validation purposes. So you are validating your understanding on the system. Another way to use a prototype is when you are not sure about a technical aspect or a function or a quality attribute such as performance issues. So if you are not sure before you commit to accept the requirement, it's a good idea to do the some rapid prototype. Okay. Now let's continue into some other classification of prototypes as rapid and traditional. The rapid prototype is the easiest and fastest way to do something. As I was saying before, maybe you just wanted to make sure that you can achieve some technical aspect. Okay. And the type of prototypes can be physical, graphical, mathematical. And on the performance part, it's very common that sometimes the users, they already have their infrastructure and they are asking us to automate something. So to improve the process or to come with a new idea, but they don't want to change the infrastructure. And sometimes the resources are all, and they may have a very high expectations on performance. So when they ask us that they want to get certain jump into the performance of some activity, it would be a good idea to do a rapid prototype to see if that current infrastructure can support the type of performance that they are asking. And we can get those answers by doing rapid prototyping. Okay. So we can use it to investigate the form and fit. This is mainly a validation aspect, human system interface, a validation aspect with the feel and look of the system. Operations and feasibility are more technical aspects, and it might be more into the verification point of view of the use of the prototype. So you want to verify that you have the technical capability to comply with that requirement. Okay. Now, one important thing is that when you do these rapid prototypings, you want to be over as soon as you can. So we are not really putting too much effort into documenting and following all the processes. So you just want to do a representation of whatever you want to prove as fast as you can. Now, because of that, because you didn't do it following a system engineering process, you should discard the prototype that you have. Why? Because it achieved the purpose. So if my purpose was to get my understanding validated, now, okay, so I just drop it, okay? And now I start from the beginning, and then you use a system engineering approach, okay? Another type of prototyping is additive manufacturing, or is also known as 3D printing. So what we can do over here, so you can create parts by adding material in a layer by layer manner, okay? So you can show something physical to the customers. They are relative cheap to build, and when they are not too big, you can do it within a good amount of time. You can do it for plastics, polymers, metals, and they have started using other type of materials, you know. Now, you might also be able to create some geometric models that if you do it using subtractive techniques, they will be very difficult to do it. So that's one of the advantages of building layer by layer, okay? And at the end, so additive manufacturing, it will be preferred over subtracting manufacturing techniques, okay? Now, on the traditional prototyping, you might want to use it to reduce the risk or certainty, okay? And we can use two types, the partial or the full prototype. Now, again, those type of prototyping, they use higher fidelity and they are interactive, okay? Now, on the partial, as we were saying before, you just focus on certain critical elements of that. And on the full prototype, you want to do the complete representation of the system, okay? And you want to be as complete and accurate as you can be. So you can imagine that doing a full prototype is almost doing like the whole system. But maybe your system is so big that you just want to do one part of it and make sure that your idea is correct, okay? So what's the benefit is collect objective and quantitative data on performance, times, and errors. And let me share an example with you, okay? And what these other things, sorry, identify changes to improve performance, reduce production costs, improve your quality, you name it, okay? So let's see one example. So we have this train, you know. So this maglev train, it was developed, and the intention it was to understand the form, the fit, and the functionality of that. So it was not intended to provide transportation. So they were not testing people coming in, coming out, how they feel inside. No, they were doing it mainly for the aspects of the whole device was working, how fast it was, you know, the safety of the device, okay? And then I have a question for you guys. So do you think is this really a prototype, or can we consider it the system? What do you think?
I think we can consider this as a prototype because considering it as a system would require understanding how it interacts with all the other interconnective aspects of the whole commute system.
Yeah, that's a good point. And the other part is that it was really a proof of concept. And it was a proof of concept because they were just building the train in two stations that were very close, but they wanted to do that to cover most of the city. So they say let's build one. Let's focus on the most important things that we want to test. Let's look at performance. Let's look at the safety. So let's look at the speed that we can get with this thing, okay? So they were testing those things in a small scale. So it can be considered a prototype. It is also called a proof of concept, but they did not, as they were saying there, they didn't test all the things, such as all the aspects of people coming in and coming out, how they feel inside. It was not tested. It was not part of the focus, okay? Now, on on modeling and simulation tools. So it says verifies and enforce compliance to the syntax and semantics and helps the modelers to create a well-formed model. So we had been talking about doing models. Now we are talking about the tools that can help you create those models. So having that tool is very important because uh, you embedded in the tool the syntax and semantics that it supports. And when you are building your models, that, that tool can help you determine whether or not it's a well-formed model, whether or not you follow the syntax and semantics when you were creating that model. So that's it. It's very important, and help us remove many defects, okay? Now, we may also have this tool support through the whole development cycle. That would be very good, okay? And we may also have tool support when we have to interact with other models. So some tool support may have import and export capabilities to be able to use some of the data that is created by other models. Or we can also import our data so some of that information can be used by other models, okay? So in this example, this is a state flow diagram. And in this tool, it's Simulink. It's a tool inside MATLAB. And the cool thing over here is that you can create your state transition model, but then it allows you to put inputs to the model. So you can execute the model. So that's something very nice. We are integrating over here the part of modeling, and the tool is helping us also to provide the part of simulation by running this model through time and by answering to certain events that we are putting, okay? Now, some of the metrics that we have for the models, they will provide technical, we might get technical and management metrics, okay? We might also use it to assess the amount of work or effort that we are investing into modeling and simulation. And we might also do it to measure that into the whole life cycle development, okay? Now, other type of metrics is that we can assess the progress of a given system development that we have. We might assess the quality of the models, or we may assess the quality of the systems as we are building that model, okay? And we might also use it to estimate the effort and cost. We might use it to assess the technical quality and risk. Um, we may determine if the performance requirements can be achieved. Okay, this is some of the examples that I was giving you before. Or we can, this is the other that I share with you, predict the number of defects in a system testing based on the peer reviews. So we can use the models in different ways, and we can get some of the data of the models to help us understand certain characteristics on the system or on the models that we are building, okay? Now, as a summary, let's see if we got it right. So what's a model? So it's a model. It's a representation of the essential characteristics of a system, its intended environment, and the interaction with other systems and users. So that's what we mean by a model. A simulation is going to be the implementation of the model into a specific context or environment and allows the model's execution over time. So that would be the difference between models and simulations. So simulations are using models and they executed over a specific time. Now, in selecting a model or simulation, the first thing that we discuss is what's the goal of your model? What do you want the model for? That's very, very important and has to be your first step to be taken. And on the second part says you need to review who's going to be your audience. What's the purpose of the model that you have? What type of information do you want to collect or do you want to share or communicate? Okay. And then the use of modeling and simulation, it should be done to enhance your learning, you know? And this is something that I would like to um, stress, you know? Some organizations, they will build the models because they have to, but they don't use them. So what's the purpose? Or some organizations will finish the phase, so they finish requirements, and once they are done, they say, where are your models? Oh, that's true, let me do those. So that is not giving you value. It is only giving you bureaucracy. So when you are using models, do it while you are doing the task. And for example, on requirements, you may think that you understand the relations, but when you start drawing them, then you might realize that you are missing some of them. And then when you are able to show it to your customers, they may also identify whether or not we are missing or we are putting things that they are not correct. So the models will help us learn more. So the models will force us to have more complete information. So use the models in your favor. Okay, don't just do models for the sake of doing models. Okay. Um, we can use modeling and simulation for verification and validation purposes, as we were mentioning before. And modeling and simulation, this is another important thing. You know, they are really good, but do not forget that they are abstractions. So what does that mean? That when you focus on some things, you discard other things that are not in your model. So even though your model may have a value, never forget that it is not complete. It is only an abstraction, okay? And we can measure the quality of your modeling and simulation. So in other words, once you have your model, can you trust it? Did you use a good system engineering process to build it? Did you get the right people to give you the information to build the model? So those are some of the questions that you may ask before you use the model, okay? And then here we have some of the references that we use in order to build this presentation. And I wanted to leave some time for you guys. So if you have any questions, please feel free to ask.
All right, guys, if you all have any questions, you could either type them in the chat box, which we are monitoring, or also you can unmute yourself to ask the question, please.
Hey, Dr. Alquindi.
Hello, yes?
Yeah, I have the question to Dr. Mondragon.
Okay, please go ahead.
Yeah, first of all, yeah, that's the excellent presentations. Yeah, particularly, you know, I learned a lot regarding the, model-based system engineering. And one of the questions actually is related to the complex system. I'm not sure, Dr. Mondragon, in terms of the model-based system engineering, is that capable to handle the complex systems, particularly if the system is relatively large?
It is. I mean, it's not easy, but we are going to have a second part of this talk where we are going to talk about explicitly about model-based system engineering. Now, in order to tackle the complexity, you need to break down the system into different perspectives.
Right.
So as we were saying, so you may have a mechanical engineering perspective. or you may have the software perspective, or you may have the electrical perspective. Now, inside each one of those, you may have also different aspects to consider. So, do you want functional oriented, behavioral oriented, data oriented? So, the idea is that as you have different dimensions, you try to find the model that is best for that dimension and work on that dimension. Now, that's going to help you tackle the complex system into a set of subsystems or set of different views and attack each one of those views.
Mhm.
Now, that also injects another complexity, and the complexity that you are injecting is what we were saying before. You got to make sure that each one of those models doing done at different levels of abstractions and at different applications domains, they are consistent, they are coherent. And that's when there is a lot of complexity on using the models. So on the next talk in the afternoon, we are going to talk about how can we tackle that and
Right.
what approach we can follow.
Okay, sure. Thank you very much. In terms of the complexity, the big system, in fact, we always count on the composition approaches, right? And then,
Yeah,
as you know, that design structure metrics actually very popular. And then, of course, there's many of the literatures have been used for that. And then,
that's
but the
correct.
thing is, for that approach is in fact they'll be very much powerful, can engage with the model basis engineering in the methodology part. So I think that's the probably this is something actually could kind of think of the what is a better way to do it. But anyway, of course, there's a lot of detail to discuss, but I just bring that up. And also, I have a second question, just not a question, but just want to ask about your opinion regarding the system-based, model basis engineering. Of course, we discussed the past, current, and beyond, right? So in terms of the future direction for the model basis engineering, of course, we want to make it become very powerful methodologies. And think of a lot of the new kind of knowledge has been developed. For example, AI. Now the AI is very popular. Data sciences, data analytic, Internet of Things. So those are very kind of the powerful technologies. In fact, it exist. So I just want to acquire your opinion with the model basis engineering. If we treat that as is upstream and downstream, right? So is any way those kind of the new kind of knowledge can be injected or be helpful to enhance the power of the model basis engineering? Anyway, this is very big, big question. So just want to learn the opinion from you.
Yeah, I think that so we are creating new models, as technologies emerging and as we are combining fields. So that's one of the challenges of systems engineering. Every time there are more domains to integrate, and the specialization in each one of those domains is every time bigger and bigger. So the idea is, how can you integrate the new models?
Right.
And then how do you do the checks to make the models coherent or to make the models consistent?
Yes.
So there is a big challenge in doing that. And that's the problem that the organizations or the companies are having. That in today's talk, keynote speaker Yvonne was sharing with us that they use different tools in different organizations. And within the organization, there is no problems, but among organizations, they may have troubles to share the models. So the integration of the models is a very, very big problem today. Mhm.
Yeah. Thank you. Thank you very much.
Yeah.
Yeah.
Thank you, Dr.
It's
Mondragon, for the input. And do we have any other questions? Oh, I see we have a question in the chat box. Let me read that out. So Raul Sanchez asks, is there any preferred software for modeling strain forces applied for printing circuit boards and electronics, more from a manufacturing point of view?
I gotta be to be honest, and I cannot answer that, you know. So the problem is that there are so many different domains, and it's very difficult to be an expert in all of them. Okay, so I would not like to say or name one, and maybe it's not the best. Okay, and I might get also into troubles of having being biased and saying one name, but you know, it's very difficult, you know. And as I was saying, when we are working on a systems engineering approach, and you have let's talk about the car. How many domain disciplines do we have there? There are so many. And each domain discipline has its own model. And there are multiple tools for each one of those models. And some of them have more fidelity than others. So I'm not an expert in that particular area, so I'm sorry I cannot answer that question, okay? I don't know if there is someone in the audience right now that might be able to suggest.
Thank you, Dr. Mondragon, for that. And then I do agree as well, because whatever type of modeling that it is we want to pursue, there are domain-specific tools in related to that, right? And then we first have to identify the purpose of which we are trying to model, and based on that is what we identify the tool as well, because there could be multiple tools in the same domain to tackle different aspects of modeling.
Mhm.
So Raul, I hope that kind of threw in a small insight from our end onto your question, but then we are indeed sure that there are multiple tools for that specific domain in printing circuit boards, but then we are not that familiar with in printed circuit boards. Yep.
Mhm.
Thank you. So if we don't have any other questions, we will be we will be introducing you all to what model-based systems engineering is in the next session. And the next session would start at 3 o'clock Central Time. Dr. Mondragon, that sounds good?
Yeah, that sounds good. So
Yep.
no other question in the chat, yeah?
Yes, we don't have any other questions.
Okay. Well, thank you everybody for attending the workshop. And on the second part, now we are going to focus on model-based system engineering. Now it's going to be better because now we understand what a model is. Now we understand what a simulation is, what the purpose are. And in the second half, we are going to look into a more integrated approach by using model-based systems engineering. Okay. See you in the afternoon. Thank you.
Thank you.
So this is the second part of the talk. In the first part, we were describing what a model is, what a simulation is, what type of relations do we have between the models and the simulations. We also cover what do you need to, that is important that you define the purpose or the goals of your model, and that you apply a system engineering approach to build your model, and that you verify and validate your model before you use it. So once that we have that background, now it's going to be easier for us to jump into the model-based systems engineering. Okay, so welcome everybody. Let's start with the second part. Now, first, let's address some of the challenges that we have in system development. So here we have from those systems design currently emerge. So from where the system design emerge. So in theory, you know, we would like to be from the architecture. But in many instances, in many places, it is not true. So it's just coming from little pieces that we are putting here and there. And when you do that, then the system is going to be breakable. It's not going to be stable. And you are going to have a difficult and complexity to test and to operate that system, okay? In addition to that, let's talk about the knowledge and investment that you do in your system development. You are creating models, and in many of those organizations, you have groups. So you have a certain group of people working on analysis, and they are doing defining the business requirements, customer requirements, and then we are jumping into technical requirements. But then sometimes that team, that group finish and give it that work to some other group. So they are working in a different phase. So sometimes we are losing information over there. Sometimes we are using different models between the phases, okay? And so by doing that and coming back from design to requirements and not having those complete models, then the costs start going up. And the other major problem is that the problems that we will find out in those models, we will find them kind of very late, okay? Now, the other challenge that we have is that every single time we have more demanding customers. So everybody is now looking for the new version of the iPad, you know, or the iPhone, or what's going to be the last version of the new computer. Okay. So we always want more, and we always want it faster. We want the new version of the new car. So the society is getting into a frenzy, into a trend that we just want things immediately. So all the time that we were investing in developing the systems, now they say you cannot take that longer. So you want to wait 1 or 2 years. When you put it into the market, now somebody else release it and we lost the market. So there is a lot of push on delivering the products sooner and sooner. Okay. Um, the other challenge is that also the complexity of the systems that we are building is growing every time, every minute, and is growing on the capacity that we demand from the systems, but it's also demanding on the interactions that we have with some other engineering disciplines. So that's what's getting the complexity and what's making it very difficult. And we are also, because of that growth, we are getting inadequate and incomplete specifications. And of course, the verifications of those specifications are getting short. Now, on the complexity of the system, you know, you need to think about all the different languages that we have, all the different technologies or application domains that we may have to consider in order to build one of those devices, okay? And also what's happening too is that the development of the systems, some of those are not done only in one system. So you may have one development team maybe in California, and then you may have some other design team, some part in Europe and some part in India, and maybe some other part in Mexico. So we have these global, the technologies are putting teams all over the world, and we need to work in an integrated way. Okay, so those are some of those challenges that we are getting. Okay, now if we put all those demands together, what's happening? What's happening is that, to be honest, we have not kept the pace. So we haven't been able to reach all those demands, and we haven't been able to deliver more capability in less time. Okay, and the problem is that many of us continue using the traditional methods, and we continue to use the traditional development teams or environments. And by doing that, um, most often we are failing in delivering our times in time and with quality. Okay. Now, let's try to understand what happened when we are developing those systems and how the communication takes place into those organizations. So mainly, all the information is driven by documents. Okay, so we are interviewing our customers and we are getting those requirements and we are creating those documents. Then what happened is that we will just put together we will stock all those documents, for big systems. It's crazy the amount of documents that you have and the amount of information that you need to read. Okay, so we put them all together and we are doing some trying to convert some of that information into customer requirements, some technical specifications, and then we pass that information to the following group. So we put it downstream now to the architects, and then for very big problems, you have even two groups, the architects and then the designers, and they are working on trying to create the models, some of those models, by reading all that stack of documentation that was delivered to them by the customers. Okay, so poor guy, can you see his face? He's just like saying what, and gotta read some of those and create some of those models. Then later on, what we have is that finally we have our prototype or we have our final product. But the big question, is if the system is correct and if the system will be able to fulfill the intended use in its intended environment. So that's really the big question. Now, let's walk through the development cycle. So let's take some moment to go through the development cycle. We are going to represent one view of this development cycle that is called the V model. And I'm going to explain why we call it the V model. And let's try to go to this model and how it should work, on the ideal world. So we will have people working on requirements, interviewing people, doing observations, comparing some technology with what's available on the market, and they will be creating those requirements, okay? And then we will do some systems analysis and design, and we are going to be working further on decomposing those, proposing a solution to the system and decomposing that. So the first level is the architecture, and now the second one is the detailed design. So we put more detail into each one of those components. And finally, we start the implementation of the system. So in this case, it's a software system, so you can start doing some coding. If this is a system engineering system, then we can start doing some mechanical pieces, some electrical boards, some software, so whatever you have in that system. Now, once you build each one of those components, what happens? Then you will have to start doing the unit testing. So each component has to be tested, and we gotta make sure that the requirements for that component are satisfied. And then before you start integration testing, you gotta make sure that that components fulfill the requirements. And another important thing, that requirement, it's satisfying the interface that was put in the detailed design. So that's something very important. Before you put components together, you have to make sure that they work by themselves, and then you gotta make sure that they respect the interface, the signature that was imposed to them by the design. So as an example, imagine that somebody is working on the frame, okay? And somebody else is working on the door. So I have a question for you guys. Imagine some of you are working on the frames and some of you are working on the doors. Now, can someone tell me whatever you are thinking, whatever you have in your head, how many interfaces or interactions do we need between the door and the frame? Please put it on the chat. Or if you want to talk, you can also share it with all the group. 3, very good. What else? Somebody else. So those 3 parts, 4, come on, somebody else, come on. So those are like when we need to put the door and attach it to the frame, we need to grab it from somewhere, yeah? So let me participate too. And I wanna say too, okay? So have you seen some doors that they have kind of pivots on the top and on the bottom? So those ones only use 2. Some doors also only use 2 and they have it on the sides, but they don't use 3. Some of them will use 3. So what if we didn't specify the number of interfaces? Can you see my point? When you come with your door and try to put it into the frame was done for 3 and you come with 2 that are on the side. Or you come with your door and you have the pivots on the bottom and on the top. So that's why it's very important. So it's not enough to check the functionality of the component, but it's also very important that we check that that component respected the interfaces imposed to that component so we can integrate them, okay? Now, the other part, once we are doing that integration, then they say that we need to do subsystem integration. So we can have integrations of component within a subsystem, and then we can have the integration of all the subsystems, okay? So this is what we can do. And the other important thing is that once you have all the interfaces ready, all the subcomponents tested, and you have, then you have to proceed with something that is called the system testing. Now you stop looking at the components, you don't care, and now you treat it as a whole. You treat it as a monolithic system, and now exercise the requirements for that system as a whole, okay? And the last part that we have over there that was the system acceptance is putting another layer of complexity. Now we need to take into consideration the environment in which this system is going to run. And for that one, if we do that, then you cannot go to your customer and tell your customer, oh, I don't know why it's not working here, but I promise that it's running in my laptop. It's like, who cares? Who cares it's running your laptop? Who cares it's running your lab? Who cares? You were not hired to build something that runs in your lab. So it's very important that at the beginning, during the requirement solicitation, we understand the environment. We understand the intended use of the system as a whole. So when we run the system acceptance, then we fulfill all those things that we have over there. Now, what's going to happen here? So once we are done, that in some occasions, unfortunately, is when we identify the problems. It's kind of late because we are identifying those problems when we are doing acceptance testing. So we are over there in the environment with the customer, and then we realize that maybe we have an error in the software design or component design. Maybe we have an error at the architecture level. Or even worse, we have an error on the requirements. Either they are incomplete maybe they are inconsistent, or even worse, we only collect the wishes of the customer and we didn't address the needs. So the problem that the system that we are doing is not solving any problem. It's just good intentions and ideas that our customer have. So at the end, what's going to happen? It's going to have a lot of rework, and that rework impose costs and impose problems in the schedules. So we got to be very careful on not waiting until the end to try to catch those errors. Okay. And some common issues is that once a document is done, that document is not updated. So even if later on we have a request of change and we accept it, we don't go back. Imagine the change happened on design. We don't go back and modify the architecture. Sometimes people don't go back and update the requirements. So if we do that, what's going to happen at the end? That your documentation is going to be inconsistent, incorrect, and of course that is going to be abandoned. So the people doing maintenance will not go back to your documentation because they know that it is not consistent. They know that it is incorrect. Okay. So at the end, even though you are following a process, you are creating some of the models, you are wasting all your effort. You are wasting all the discipline that you try to follow in your development cycle. Okay.
Please.
Do you have a question?
I'm sorry to go back to the door.
Yeah.
The definition of interface, the way I would infer from the definition of interface that it's not only hinges, but some kind of locking mechanism without which a door is not really functional. So isn't that understanding that kind of understanding I would think would be important to be effective in your documentation. In other words, go ahead.
Yeah, so what is very important is that we keep the documents alive, and that when we accept a request of change, we do our job to understand the impact into requirements and whatever artifacts are going to be impacted, and then put the effort to work on those and have those documents updated. This is what we need to do, and this is what is being suggested in some of the methodologies. Unfortunately, in the real life, many people doesn't do it.
The confusion being is one person thinks 3 interfaces are latches or hinges, and the other person thinks 3 interfaces are 2 hinges and a latch.
Yeah. Yeah, that's correct. We might also have some ambiguousness on defining the things. And I'm going to move over later on the need of the models, and not just to rely on the textual description on the systems, but trying to move more into a more uh, formal description of the system by using the models.
Thank you.
Thank you for your comment. And please, everyone, please feel free to jump in at any time, okay? Now, talking about coupling with the current complexity, okay? One way to do it is that some of the development methodologies or life cycles, now they are putting into consideration the iteration and the recursion of the concepts that you need to apply. So for the iterative part, so let's imagine that we have a system of systems. So we have a system that is made up of many systems. And we start like the analysis of that thing, we have to pass through 2 main stages, concept definition, and then let's call the other one system definition. And within that, we are running different processes. So if we start on business or mission analysis for that system of systems, once we are done, then the results, they it will send us into stakeholder needs and requirements. So here we may use cases or histories or things to let us understand how the users or some other devices might be interact with our system, okay? And we should have gates at the end of those stages or phases, and make sure that if we find errors, we can come back to the previous phase. So if we find them, we go back, we rework on those, and then come back. Then if we move to the following phase of system requirements definition, well, also at the same time, we kind of start identifying some of the systems that belong to that system of systems, okay? And again, if we find errors during the gate, so gates are reviews that you have at the end of that process or the phase or the stage, whatever you want to call it, and make sure that the word is correct. If not, then you gotta go back, okay? And again, we keep providing now some requirements definition for those systems of interest. We continue with the architecture, we'll find errors, go back and continue feeding information on the system of interest. And then we continue with the design and definition. So again, we have, it's another milestone. We conduct our gate activity, our review, and we find errors and we may have to go back to architecture. Now in real life, you don't always go back to the previous phase or activity, yeah, whatever you call it. But it might be the case that you gotta go maybe one behind, or maybe you catch over there an error that it was introduced from the beginning, from the business analysis part. So you gotta be open to these iterations. So the development nature of systems is iterative, and that's something that we need to understand. Sorry, hold on. Sorry, guys. Those are the things that we need to deal on working from home, okay? Sorry, it was my dog. So on continuing, so we have to be open that it's impossible to get all the information from the beginning, and we are using different points of view as we are moving towards the project. And also we are human beings and we are inserting defects. So we gotta be open to do those reviews, catch as early as possible those defects and go back and fix them. And if we catch an error later on in the life cycle, we gotta be open to go back to whatever we injected and update the document and check what are the collateral effects of that change over some other phases, okay? Now, for one of those systems of interest, we might start decomposing it and following again the same process. So going over business analysis for that particular system of interest, stakeholder requirements need, and doing the same thing as I explained before. And so as we do that, this is the part that we are going to call recursion. So we were first at the systems of systems. Now maybe you are at the system level and you apply again the process at the system level. You might find errors over there and you may have to go back at the system of system level and let them know that maybe an interface or maybe some of the requirements is not feasible. So you are coming back. Then once you fix it, you come back over here. And while you are working in this system of interest, maybe you realize that that system is still very complex and you will have to decompose it into subsystems, okay? And maybe working in one of those subsystems then you find again some other errors that were at the system of system level, and you have to come back. So what we need to understand is that developing a system, there are two things happening: iterations happening between the same level of abstraction, and recursions by going at different levels of abstraction: systems of systems, systems of interest, subsystems, components, and then even for a component, you may have to follow the same development cycle. So we gotta be open to understand that we may have to repeat activities many times, and that you may have to apply all the whole concepts at different levels of abstractions. And that's what kind of gets complicated and difficult to work on this. Another way of coping with complexity, it was done by the spiral methods. And they were done specifically to cope with the uncertainty. And you may have uncertainty, for example, on the requirements. Maybe you really do not understand the problem, and you need to give yourself an opportunity to start working little by little, maybe with the small prototypes, to gain some knowledge in that application domain or whatever you are working. It might be also the case so that you don't know the application domain, or there is a new technology and you don't know that technology, or it might be that the requirements are not clear and they would be evolved as you are knowing more and working with this application. So they will help us on the exploration, on the evaluation, putting more information as we are learning of that. And once you reach certain level of understanding, or you were able to mitigate some of the risks on technology or requirements evolution, then maybe later on you can even jump into a more structured life cycle model, okay? Now let's do an exercise. And now let's jump into a different topic. Now let's talk about how it feels to communicate, to collaborate using text, okay? So I call it this collaboration in text in action. So let's try that a little bit. And I will need your help. I need one volunteer that, if you could please read the text.
Okay, I could do that.
Okay, please go ahead and hold on. And
Yes.
everybody will listen, okay, what they are telling us. And when he is done, then we will say, of course, I know what is he talking about. And then you guys somebody else will explain it back to us, okay? So please go ahead.
All right. The device manager sends a request to the transaction manager that will put the transaction manager into a checking state from what it was before, which was idle. The transaction manager that sends a message to the account manager to get authorization and waits for a message to come back. If the authorization doesn't come back within 2 seconds, the transaction manager sends a denied message back to the device manager. The device manager will have started in an idle state, but after it gets the confirmation, it should move to a state where it waits until it gets the authorization. If it instead gets a denied message, then it should move back to being idle. All this should happen in less than 5 seconds.
Okay, I think it's crystal clear. So someone would like to say it back without reading it?
Anybody?
Anybody? Come on. Or is the rest of the audience like this?
You want us to read the next paragraph?
No, so like, that's just the only paragraph, okay? So what most of us is doing right now is like, what? Yeah? And what we need to understand is that really communicating the requirements in text and reading all these pages, it gets very complicated. And there is no way to remember all the details. So it's very easy to get into troubles if we only rely on the textual description. Okay, so then why do we use a diagram? Okay, and then that person, okay. So let me send you this diagram. And now they send us this diagram. Now, what about, is it clear? Is it clear now? Or is it better? So it depends. So the answer is that it depends. Why? Because, well, first, instead of reading the text, if we have a visual representation of what they were telling us, it will help us. It is more natural and it's more intuitive, but there are some restrictions. So this guy can say, oh, now I see it. If and only if, you know, he knows the syntax and semantics of the diagram. So if he has been trained or she has been trained on using these models and they know the syntax and semantics, now they say, oh, now it's very clear. So for example, what we have on the top are the name of the objects that interact in that transaction. What we have with the hexagon over there are the states in which that object it has. And the lines with the arrows, they represent the messages that are sent to those objects. And then if you go from the top to the bottom, that represents how the time flows. So we know then that the first message, it was the request. And then the second message was the confirmation. The third message was the request, the check. And then we have the transaction manager that is calling a function to itself. So he's calling itself to send a message and he's reacting to the message. And then on the left part between the 5 seconds, what we are saying is that between the request, yeah, and at the end of the transaction, it has to be, it says less than 5 seconds. So by learning what the components of the models are and their syntax and semantics of those components, then the diagrams become very easy to read. And I think that you may agree with me that it's easier to review this model and kind of recall how is it working rather than reading the text. Do you agree?
Yep, totally.
Okay, so now let's continue, okay? Now talking about graphical abstraction, it really depends on the application domain that we are working. So in my case, I did a bachelor's in communications and electronic. So the ones on the left is obvious, you know? So it's very easy to understand. But I'm not a chemist. So maybe the one on the middle, maybe I'm not that familiar with that one, okay? And people working on manufacturing and using all these tools, you know, for the components and the interactions, and they can also get the heat or the strength of the pieces. So it's natural for all of them to use those models, okay? Maybe we have an architect within us, you know, and for them, those are the type of models that they use, yeah? Or maybe we have a mechanical engineer and he may be a lot more familiar with these type of diagrams. So based on the application domain that you are working on is the type of models that you use to represent the characteristics that are important based on your application domain. Okay? Now, let's talk about the support into the life cycle. And here we have a very high level, you know, so the concept, the system development, then we get into production, and then we gotta go into operations and support. And so for that support, we want to support that life cycle using models. So what we want to do is to do this approach that is called model-based system engineering. And let's read the definition from INCOSE. So they say, it's a formalized application of modeling to support systems requirements, design, analysis, verification, and validation activities. And we are going to do that through the whole life cycle phases, okay? So it's not just for one of the phases, and we want it for all the phases, okay? Now, we also need to be careful about the levels of abstractions of those models may have. And we also need to open ourselves to the different domain applications that we may have, okay? So like in this case, we may have some operational models. And for those into architecture of systems, we have some frameworks and you have different views, and you may have the OV1 and then some requirements models, behavioral models, okay? Then, so you have the operational views, you have systems models, and then you may also have components models, okay? So different levels of abstraction. Now, the definition on the top, more simply, we can understand it like this. Model-based system engineering is the formalization of the practice of system development through the use of models. So we want to make sure that we are following a system engineering process, and we are going to support that process by using different models, okay? Now, what's the scope? What's the scope of model-based system engineering? Well, as we were saying before, you know, is to integrate multiple modeling domains, you know, mechanical, electrical, in across the what? The life cycle, okay? From systems of systems to components. So the last part of that definition is telling us that we have different levels of abstractions, system, subsystem, component. And the first part is telling us that we're gonna be open, not just to see the system from one application domain, but we gotta be open to the different application domains, okay? So I have a question for you guys. If we want to develop a car, please put in the chat, what application domain do we need to consider? Please, everybody, start typing some applications domains that we need to consider when developing a car. Okay, we have 1 minute, come on. Go ahead, please. Constraints, those are things that we need to consider. But talking about application domains, for example, we need software engineers, okay? What other engineering domain do we need? Or some other domain that might not be hydraulics. Okay, very good, electrical. What else? Very good, what else? Very good. So I have a question for you guys. Do we use the same model? Yeah, that's right. Of course, no. So each one of those domains, they are looking at different characteristics of the systems, and they are using a tailored model for each one of them. Okay? That's very true. Okay? Very true, Ronaldo, in your comment. Okay? Now let's continue. So what's the goal? So what's the goal of model-based system engineering? says facilitate results in quality, productivity improvements, and of course, we want to lower the risk, okay? Risk of failure, you know, in our system. Now, talking about the specification point of view of the product or system that we are developing, model-based system engineering is going to help us on capture the information, on doing some data analysis on some of the parameters or aspects of the project. It will help us to share the knowledge within a domain and across domains. And it will help us manage the complexity by decomposing the system into different domains and having models for each one of those domains, okay? Now let's discuss the characteristics of model-based system engineering. And this is something very important. We are trying to push what we are going to call model-centric and not diagram-centric. And let's try to explain this. So on model-centric, it's an underlying model of the system, okay? Not just putting together a couple of models that somebody else did or sketches, okay? We also need a common repository that is going to host those models, okay? So that they have to be in a common repository. Everybody working on the project should have access to those models. So it's not like I did it for me and nobody else can see it. No, we are doing that in order to support the development of the system. And we also need to help other engineers to understand what we are doing, okay? So at the end, by working on a kind of big model made of small models, yeah, or complementary models, and having everybody access to it, we will achieve having only one through, okay? One through that is built by all the views of the model and share between all the team members of the model, all the team members of the project, sorry. Now, another important thing, I don't know if you remember in the morning talk, what Yvonne was saying. Oh, you know, I'm building some of those models, but if I want to create this table, I pull it from my system. Or if I want to get that interaction, I just get it from my system. So certain relationships, tables, or views that she needed, she was not building them by hand. Nobody have done it. But the tool will look at the data that you have in the model and is able to create some of those views. And the important thing is that I'm saying that they are created from the model. So it's not like somebody else is doing in their own computer and that computer is not connected to the internet and is not synchronized with some other models or changes that was done in other models. No, we should not work like that. So we should invest of having a common repository, feeding that repository with the different models from different application domains or different characteristics or aspects that we are interested. And once we have some of those models, we can create the views that we need, okay? Now, by using models, as we saw in the first part of the talk, those models have syntax and semantics. And by using that syntax of the semantics, we are getting rid of the ambiguity, okay? So the people will be able to understand the same thing by reading those models, okay? And by having all this set of models, or having the capability of creating views, is something similar to say that we have created a prototype and it's kind of a virtual prototype, and whatever view or thing you want to see from that system, we can pull it from the tool. Okay, so that's one of the advantages of the model-based system engineering. And here, there is another way to see domains. So some people will say, oh, we have the requirements domain. We have the guys that just think about behavior. No, we have the guys that just care about the architectures. Or we have another set of group of people just thinking about verification and validation. So you may have those kind of subgroups within your organization while you are developing a system. Now, to use model-based system engineering, all this is, so this is what we need to do, you know. All the models that we did in the different domains, they have to be integrated. It has to be some connectivity between those models, and most important, we cannot have one true in one model and a different true in a different model. So models have to be consistent within application domains and across application domains. And that's what really makes very difficult to achieve model-based system engineering. So how do you integrate those models that are coming from different perspectives? Okay. So maybe for this talk, some people believe that model-based system engineering, it was just about doing models. Just do a model, do a sketch, drop it over there, and then it's model-based. Now we're trying to move apart from diagram-centric into a model-centric. So in the model-centric, we will develop a central model for our system of interest. And we are going to focus on certain characteristics of those systems, okay? And so some of us will be saying, I thought that we just need to create the sketches and put it all together. I thought that was model-based system engineering. And no, this is not model-based. So model-based system engineering will follow a model-centric approach, okay? Now, what we want to say over there. So imagine that what we want is to have different engineers working on the system, but not by themselves. What we want to do over there is that we want to take an organizational effort to get those people working, having an inclusive repository that each one of them can use, so we can share the knowledge and put all that knowledge into a single repository representing kind of a single big model for the system, okay? So while that model is made of different models from different perspectives. So, sorry, let me back up and let me try to explain it in another way, okay? So what we want is that since we start doing requirements gathering and interviewing the people, doing observations, understanding what's going on, try to feed that information into what we are going to call is the model-centric, the model that we need, okay, for our system of interest. And so all the diagrams that are done by the analysts are feedback into this model. Any behavioral analysis that is done is connected to this model. So I have a question. Can you see my mouse moving or not?
Yes, we can.
Okay, very good. So what I want you to notice is that those models are not living by themselves. Those models are connected. There are certain elements in those models that might be related to more than one diagram. So that's something very important to understand. So we are not just putting models and those models are not connected. If a model is describing a certain element or component, then we need to identify the component, and maybe that component is being viewed by different models. So that's the important thing, that we identify how the elements are connected and which type of views we can use for a given component, okay? So then if we do some architecture, we also need to put that information back into our centralized repository. And we can also do the same for verification, you know, or whatever results we have on verification, some models that we build for verification, we put it back into the model. And then whenever you want to get some information, then you query your repository and build whatever you want by querying that repository. And that's very important, because then it's going to be consistent and it's taking into consideration the different views that you have for your model. Okay. Now let's talk about ambiguous. And what does ambiguous means? Is that anything that can lead to multiple interpretations. And I have a question for you guys on the topic, on the green topic that says what? So what do I mean? Do I mean A or B and C? Or do I mean A or B and C? So let's put it in the chat. Which one do we mean in that sentence? So one example may be that I meant A or B and C. Can you see it in the chat? Can someone come with a different interpretation? Can you put it in the chat? So I'm asking if you can read that. Very good. Thank you. Thank you very much. Yeah, that's the other possible interpretation. So we'll say, no, 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 no. What we meant, it was A or B and C. So if we put that in text, there is no way to distinguish it. Maybe if someone was reading it and used intonation, maybe we can get it by the intonation. But if you are just reading a document, you know, there are multiple interpretations. And that's what happened when you are using natural language. It's open to ambiguity, okay? So this being ambiguous when we are creating the specifications or the definition of a system, it really wastes both time and money, because we gotta go back and say, no, you know, this guy didn't meant A or B and C, but he meant A or B and C, you know? So it creates a lot of rework. And you know what, guys? Some of you, sometimes also we have some attitude problems. And some of you that read it as A or B and C, you will say, I'm correct. And the other group of people that read it as A or B and C, they will say, no, I'm correct. And then you get more into dumb fights on who is right, better on trying to understand what's the correct thing. So we are kind of just getting into political games that are not good for anyone, okay? So as a summary, we should learn that using natural language, such as English, is error prone to ambiguity. And here are some more examples of possible sentence that will inject and ambiguity. So I have another one for you guys, another phrase that is used a lot, in requirements, elicitation, and people repeat it a lot. And the phrase says something like, we need to build a system that is easy to use. So can someone please explain that to me? So where is the ambiguity part? Let's put it in the chat. Where is the ambiguity part? What else? So the end user, where else? So a system that is easy to use. What is ambiguous about that? Yeah, very good. So easy to use for whom? And then the other thing is, what does easy means? Okay. And if we do not go into that and ask for explanation, you may have your version of your truth of what easy means, and your customer may have a different version of the truth of what easy means. So then what do you mean? Do you mean that we offer help? Do you mean that we provide hotkeys for some of the commands? And do you mean that we provide guidelines in how to run each one of the steps? Do you mean that every command is reachable in no more than 2 steps? Do you mean that we use big fonts based on the type of user that is using the application? So the truth is that it's very easy to get into ambiguous requirements, specifications when we use words that may have multiple meanings. Okay. Now let's continue. And so what we need to do is to promote continuity, no ambiguity. And one way to do it is, as we learned in the first part, let's use models. Let's use models that have very well-defined syntax and semantics. And if we train the people to read those models, then that's how we fight or cope with ambiguity, okay? Now, what type of defects we can get by using those what type of defects we can catch now if we use models? So if we now have well-defined syntax and semantics, and we have a tool that helps us to run the model, the tool can help us identify incomplete interfaces. So we have components that are connected to no one, then we know that we are missing some of those. We may have certain behavior that has not been allocated. So for example, Yvonne in the morning was showing us a traceability matrix where she was having, for example, functionality and some systems or components, and she was able to identify that some of those components didn't have any requirement. So that's one way to easily identify that some behavior has not been allocated, okay? Now, we may also have requirements that cannot be verifiable, and we can catch it by the type of words that we are using or some things that are missing, okay? And we can also have some parts that have not been documented, and we can identify them. Now, why is it important to identify those defects? Now, on the right, you have a graph that on the x-axis is moving towards the development cycle. Analysis, design, implementation, production, and fielding. And on the y-axis, you have how much does it cost to fix it. So the later that you find the defects, the most cost that it has on your development cycle and in your product. So what you gotta do is try to identify defects as soon as you can. And by using some of the models and having tools to allow you to identify inconsistencies or completeness aspects in your models, it's very useful. Now, we have this example here. The automated teller system shall respond to the user's query within a reasonable amount of time. Can you guys put in the chat why is this requirement ambiguous? Very good. So how come reasonable is not clear? So what is not clear for you? What part of reasonable is not clear? Or what do we need to do to address that problem? Very good. In other words, what we need to do is that we need to quantify the requirement. Do you agree? So I put it in the chat. So we need, the requirements have to be quantifiable. And that word reasonable is not quantifiable. So if I want to write a test case to verify this requirement, I will not be able to verify it because I was not able to quantify reasonable. So we gotta go back to the customer and discuss a little bit more on what does that mean, okay? Now, let's continue with this idea of our integrated model, okay, on this model-centric approach. And now let's talk about the how the viewpoints can be generated from the model, okay? So something very important is that the different models that we were creating for the analyst, the architect, the design engineers, the testers, all those models have to be consistent, okay? And the other important thing is that if we accept a change into the system, we need to be able to understand what the impact of that change is. And if we recognize the impact in one of the models, we should trace back to the other models to be able to identify the impact to some other models of use. So what are we talking about? Imagine that we are already in the architecture phase on your system. So we did customer requirements, we did some prototypes, we did some system specifications, and now we are moving into the architecture. And we are very happy now working on the solution of the system when all of a sudden a change arrived and they want us to change one of the components. So we will have to reflect that change into our database. And we will have to identify within the database the elements that are affected by that change. And thanks to the relations with the other models, then I should be able to identify that my requirements were affected in one of those components, that when I do in the behavioral analysis, I have also a change over there. And even if I already have some test cases or I have a model or a simulation to verify that component, I will have to change it, okay? So that's the real advantage of having this model-centric approach, that you have only one view of the truth and that you can identify the interactions between the views and you can use it for doing the impact analysis when you are reviewing a request for change. And don't forget that the other big advantage is that whatever documentation you want to get, whatever view you want to get, you pull it from the model, Okay, so that's very, very important to keep it consistent. And now in this part, we have kind of a summary on the benefits of model-based system engineering. So of course, we are improving the communication. That improved communication is within the development team and also with the customers. So as Yvonne was sharing with us in the morning, you know, they use the models, they show it to the customers, they train the customer, work with them over the meaning of the models, and they can get feedback from the customers. Okay, so we can also have models for the planning part, so we can help project managers. They can also visualize the level of effort and what parts of the system has been done, and between system engineering, hardware engineers, software engineers, the testers, or any other specialty engineer that is working on the project. The other important thing to remember is the ability to manage the system complexity. And one way to do it is by allowing multiple views and perspectives of the system. So what we are doing is we are decomposing the system into different application domains. And within an application domain, we can also break down that system into levels of abstractions at the system level, subsystem and component, okay? And now on improved product quality, because we are using models that have a well-defined syntax and semantics, we are getting rid of the ambiguity, okay? So we have a more precise model, okay? And also, thanks of the semantics and syntax that is well-defined, if we are using a tool, we can use the tool to enforce it. And then we can find errors in the models that do not comply with the syntax and semantics. Okay, so that's very powerful. Now, also some other tools that you can use to run your models helps you a lot. So for example, in the morning, I was giving you examples, I think, about PetriNets. No, yeah. So on the PetriNet, that you are getting a lot of events and transactions and you want to understand how things happen, the tool can allow you to run reachability model, a reachability study. So what does that mean? Whether or not you can achieve a certain place using the PetriNet. We can also use reachability analysis on state transition diagrams. When they become really complex, for example, you want to make sure that it doesn't matter in what state the system is, you should be able to reach a safety state. So for certain type of systems, that's very important and it's mandatory that you should be able to find a safe state from any state that you are in the system. So using those tools to run those type of exercises is very powerful. In the PetriNet, you can also run queries for liveness. And what does that mean is there such a execution of the system that will get you into a state that you cannot go forward. So you are waiting for something else, the design was grown and you got stuck. So catching those type of errors manually is very, very difficult. And having the tools to find them, it's a bliss, okay? And especially when you have a lot of components in your systems. Now, the other part that we have is it says an enhanced knowledge to capture, so we can capture that knowledge. We can enhance the way we capture it, and we can also enhance the way we reuse it. So that's a powerful thing by using the models and have a centralized model when one of the components may have information that might be useful for more than one model, okay? And on the part of teach and learn system engineering, you know, it's by following the process and using the models, it's a better way for people to understand what are we doing, okay? Now, one other thing is the between model-based system engineering, we have methodologies. So let's read the definition of methodology. It's a collection of related processes, methods, and tools used to support a specific discipline. So that's a methodology. Now, model-based system engineering, it says the collection of related processes, methods, and tools used to support the discipline of system engineering in a model-based or model-driven context. So that's the definition for model-based system engineering, okay? Now, as an example, what you are looking at here is one system engineering development life cycle. It's called object-oriented system engineering. And what we are putting over here are one of the main activities. So you will have to manage the whole system development and you will have to create a plan. And for example, you will have to schedule the activities for doing systems requirements, and you will have to schedule the interviews, the creation of the models, documenting. So all that time, stakeholders working on it, it has to be planned. Then once you do that, once you have the requirements and you create the designs, then you can go into start building each one of the components that you have. And later on, you will have to do remember the unit testing, integration testing, and system testing. And what we have over there is kind of the shape of a V as the one that we saw before, okay? On the left part of the V, you are building things, and on the right part of the V, you are doing the integration and testing of the things that you were first designed and then built, okay? Now, continuing with this example, let's see how can we integrate model-based. So on the upper part, we have some of the main activities, you know, analyze stakeholder needs, analyze systems requirements, define the logical architecture, synthesize candidate physical architectures, and then some other activities that we might use, you know, to support that process. So how can we optimize the analysis of alternatives? So for example, in the design, you know, you are building a couple of architectures and you need to select the best architecture. So you can use some of the models to help you understand which of those has a better performance, okay? Now, on managing requirements traceability, in the morning, Yvonne was showing us how the tool support that. And we can have traceability, for example, from use cases into requirements, you know, technical requirements. And then you can also have a trace between the requirement and the component that is addressing that requirement. And you might also have another one between that requirement and the test case that has been done to test that requirement, okay? So you can have full traceability between each one of the elements that is built as you are moving towards the life cycle. So that's the idea. You have a system engineering process that is being supported by different models in a centric approach using this model-based system engineering. And now as a summary, you know, so let's see what we learn. So we have model-centric versus documenting-centric. And what do we learn? That model-centric will replace document-centric. Document-centric, you only have models done independently and they are not connected. Nobody checking for coherence or consistency, okay? Document-centric, the pieces that you are building in the models, they are safe, you know, as elements. And some of those elements might help you build more than one model, more than one part, or have a different views of one of the components. Okay, so that's where the power is coming from model-centric. Now, model-based system engineering involves is really the formalization of practice of system development through the use of models, okay? And what is it going to facilitate if we use a model-based system engineering? The idea is that you increase your communication between all your stakeholders. It's going to help you to manage the complexity of the systems, and it's going to give you support for consistency and error checking in the models that you are creating. And then finally, by following this model-centric approach, we are removing the ambiguity. We are ensuring that there is only one version of the truth because all the models are in this unified repository and they are consistent. And the other part is that this repository, can be used by all members of the team. And the most important thing is that the views are built from the model. And with the support of model-based system engineering, many of those views can be done automatically by using the tool. Okay? And then we just have the reference. And if you have any question, please feel free to ask.
Let me, I wanted to kind of put in a couple of points before we open the floor for questions.
Very good. Please,
Oscar, please correct me if I'm wrong. So for the whole shift in model-based systems engineering to apply model-based systems engineering, there are several, I wanted all the participants to know that there are several languages to do that. And then there are several modeling tools to implement those languages. So please don't take away that model-based systems engineering is creating models for complex systems using a specific tool or a language, but then it is use of models using multiple languages and tools that are available out there. So for example, we have multiple languages such as UML, known as Unified Modeling Language. We have SysML, that is Systems Modeling Language, as most of you guys may be familiar with. But as systems engineers, we tend to use SysML a lot because it's a language that helps us to specify information and knowledge, if you may, for application towards developing systems such as specification, analysis, design, verification, validation, hardware, and also including personnel, procedures, and facilities, right? But then there are also other modeling languages such as object process modeling that I have recently come across. And then there are several tools tailored to implement these languages. And each and every language I think the whole goal for each and every language is to provide a common syntax and semantics for everybody to understand what the model is conveying. Oscar, am I correct?
Yeah, that's correct. And when you apply system engineering, you see it as a high level, at the system level. But then when you start working on the architecture and the design and you identify the components, some of the requirements are going to be allocated into components that are electrical components. And some of those are going to be physical aspects that you will have to build. So manufacturing. And each one of those components that are targeted to a different application domains, they will use their own tools. So like, for example, you might build a component. So you have your CAD tool and you are specifying all the elements of that component. And then you can do some stress testing on the component. How much heat you can get into that component. How much weight it can support that component. And then even some of those tools will allow you to create 3D representation of the components. And then they can print a page, a white page with some information in the model. And then by using your phone, it's kind of reading what is over there, and you can have a 3D representation of the model, and you can use that for your customers. So really, each one of the application domains may have its own set of tools that are very valuable for that application domain. Now, the trick over here is how do we integrate some of those views? And how do we make consistent some of those views? So like some characteristics maybe on the size, on the weight or certain things that we are using for one model, those information that describe the component can also be used for other views or models. And that's where the problem comes. And here I think that's the major challenge that we have as a discipline. How do you integrate the tools? How do you integrate the models between the tools?
Exactly. Thank you, Oscar, for your insight. Now we open the floor for questions. You may feel free to unmute and then ask questions. If not, please feel free to type away in the chat box. Well, looks like we have no questions, Oscar. So it seems the presentation has been very productive and fruitful.
Okay. So are you still there, guys? Were you able to, did I explain myself? Were you able to learn something?
Yes, Dr. Mondragon is very much informative. In fact, I really learned a lot. I'm pretty sure that our students also learn a lot from you. Thank you so much.
Okay. Thank you, guys. Thank you for the opportunity.